Welcome back. In the last lecture, we saw an example in which a machine learning model that was fit very closely to the training data, that is, achieved a very, very high score on the data that we allowed it to see while fitting or training the model. That model, despite the fact that it did so well on the training data, was very, very poor at predicting fresh, unseen data. That example was kind of theoretical in nature, right? Like we made some synthetic data and we used a machine learning model that no one really uses these days precisely because it has such bad overfitting qualities. And this was because I wanted to really vividly illustrate the phenomenon of overfitting to you. However, overfitting is not just a practical concern, it's not just a theoretical concern, it's extremely, extremely practical. And in this lecture, I'd like to show an example of how it can arise in the wild. For example, in our Titanic data set. So we're going to revisit predicting survivorship in the Titanic data set using decision trees. And we're going to see that the phenomenon of overfitting pops up even here as well. So we're going to import our usual libraries. So I need NumPy, matplotlib, import canvas as PD, and from matplotlib, import pyplot as plt. You can see I've been typing these import statements too long, and I need to import here. Okay. So now I'm going to read in my data after I fix my typos. So I'm assuming that you've run the retrieve data function from the notebook ml_3.ipynb. That will retrieve the data and save it as data.csv. So I'm assuming you've already done that. I have, and so I'm just going to do pd.readcsv data.csv to read in my data, and then I can inspect the result. So here I have my familiar Titanic data frame with all kinds of information about my passengers on the Titanic, as well as the column that we're going to try to predict, which is the survived column, indicating whether or not they survived on the Titanic. So recall that we diagnosed and observed overfitting by testing our model against some new data that the model did not have available to it when we were fitting or training the model. So what we're going to do here, since we don't have any more data, this data is all we have, what we're going to do here instead is split our data into two parts. One part of the data will be the training data. The training data is what we use to fit our model. On the other hand, we'll also have another part of data, which we'll call the testing or holdout data. And this holdout data will be used to evaluate the model later. And in particular, it will help us to understand things like overfitting. So the way we can split our data is very simple because the good people at scikit-learn have given us a nice function for this. So I need to import from scikit-learn.model_selection. I need to import the function train_test_split. Then I'm going to split my data randomly. So I'm going to take a random 30% of the data and put it in my holdout or testing set. In order to promote reproducibility here, I'm going to reset my random number generator so that if you run this notebook, you'll get exactly the same results. And now here's what I do. I create two data sets called train and test. As the output of train test split, Titanic test size equals 0.3. So this corresponds to holding out 30% of the data. So now let's just check train and test what size they are. These are both data frames. And they have, you can see that the train data frame has 620 rows. The test data frame has 267 rows. So I now have two data frames, one smaller than the other as per my specification. I'll use the train to train my model or fit my model, and I'll use test to diagnose overfitting and understand how my model performs on unseen data. Now, Before we're ready to do this, you might remember that we need to do some data cleaning. So we need to massage a few columns, and we also need to split the data into predictor variables X and target variables Y. So let's write a function to do that. So we've already seen pre-processing. So from scikit-learn import pre-processing, and this is used for coding qualitative variables in quantitative terms. So I'm going to write a function, prep Titanic data, that operates on data df. And the first thing I need to do is I actually need to make a copy of data df. And this is because matplotlib will complain if I try to modify a data frame directly within a function. Instead, I'm going to modify a new copy of the df. So data df.copy. So now I'll make my label encoder, le equals preprocessing.label encoder. This is for coding the sex column and changing it from male or female to ones and zeros. So df sex equals le.fit transform df sex. So these two lines convert male, female to 1, 0 in that column because my algorithms want to use numbers, not text. They don't know what to do with text, but they do know what to do with numbers. Okay, next, I don't need the name column. So I will use df.drop to remove the name column from axis equals 1. So when I say drop name, pandas thinks that could be either a row or a column. So I specify axis equals 1 to make it clear that what I want to drop is a column. Next, I am going to split into the predictor and target variables. So split into x and y. So I will do x equals df.drop. Survived, I don't want that column anymore. Axis equals 1. Dot values. I think I actually don't need to do the dot values conversion here, so let's just skip that and see how it goes. And then y equals df survived. And finally, I'll return x and y. So what do I have here? My function will take in a single data frame, clean it, and then give me two new objects, x and y. The way we use it is by taking our train and test data that we made above and converting those into x-train and y-train, so the predictor and target variables for the training data set. So we'll do prep Titanic data on train. And then similarly, x test and y test are the output of prep Titanic data test. So when I run that code, I can just check now that for my training data, I have this data frame with all of those numerical variables now, including the ones that were text variables that I recoded. And then similarly, y-train is a pandas series of what I'm going to try to predict. And then x-test and y-test are similar, but I'm just withholding them from my model. I'm not going to use them when I do my fitting. Okay, so now we have prepared our data and we are ready to fit a classification model. We've already used decision tree classifiers in a previous lecture, so that's what we're going to use here as well. As you might remember, the decision tree classifier allows us to specify how deep the tree is, and that corresponds to how many different decisions the tree is allowed to make. So max depth large means large complicated trees with many decisions, whereas smaller max depth corresponds to fewer decisions and therefore much less complicated trees. In this way, max depth is really a model complexity parameter. It controls how many decisions, how much room for maneuvering, how much flexibility the model has to fit the data. In this way, it's not mathematically the same at all, but big picture, it's similar to the degree that we used in polynomial regression. It controls how flexible or complex the model can be. Okay, so let's go ahead and try this. I'm going to grab from sklearn import tree. And then I'm going to make a tree model. So T equals decision tree classifier. And we'll use a max depth equals 3 to start with. And let's take a look at what happens when we fit the data on X train and Y train, and then score it on X train and Y train compared to X test and Y test. So this is a relatively small max depth. And what we're hoping is that the model's performance on the training data will be similar to the performance on the test data. It won't be like the really wiggly line from before in which the model actually did worse on the unseen predicted data. And this is roughly what we see. We see that the model achieved a score of 83% accuracy on the training data and 82% on the test data. So this is pretty good. We don't think our model is necessarily very badly overfit because we can see that these are pretty similar. It does about as well on the unseen data as it does on the seen data. This is the mark of a model that is not suffering from overfitting. You're doing about as well on the unseen data as you're doing on the data that you've already seen. On the other hand, we can also use a much higher max depth, and this will allow us to do better on the training data, but it can actually hurt us on the testing or validation data, so the testing or unseen data. And this is really what overfitting is all about. So I'm going to make a new decision tree. T equals tree decision tree classifier. This one has a max depth of 20. So this is a much more complex model. It's really very flexible and very able to fit the data. So if I do t.fit x train y train, and then I'll do the same scoring from before. I'm just going to paste that code in. Now, this is pretty interesting. So what I observe is that I can get up to 99% accuracy on the training data, which sounds really exciting. But notice that this model actually does worse at predicting unseen data. It's not as bad as the polynomial regression example. It's better than useless. 76% prediction is still something. But we've actually done noticeably worse than we did with the simple depth 3 decision tree. So increasing our training score has reduced our test score. We are overfitting. Okay? So let's take a slightly more systematic viewpoint on this. We're going to look at all the possible depths and see what happens as we allow the depth to increase and train our model. So we're going to do figure now. So fig in x equals plt.subplots 1, and let's make a nice big figure. Fig size equals 10 and 7. And now we're going to look at all the possible depths between, let's say, 1 and 30. Okay, so I'm going to copy and paste a little code here. So I'm going to take what I've done previously, and instead of max depth equals 20, I'm just going to say max depth equals d. Then each time I do this, what I'm going to do is I'm going to scatter the training and test scores against the depth. So I'm going to do x.scatter d, and then I'm going to take the training score here, and then I'll plot those in black. And then I'll similarly plot in red this time for visual distinction. I'll plot the testing scores. And then let's just add some axis labels. Label equals, so on the horizontal axis, I'll say that we're looking at the complexity or depth. And on the vertical axis, I'll say that we're looking at the performance or score. Okay, so what am I expecting to happen here? I'm expecting to find a point where improvements in the training data no longer pay off in terms of the test data. And that's exactly what we see here. Remember that the black dots are the training data, and we can see that as we, or the training scores, sorry, and we can see that as we increase the depth of the tree, the training scores keep going up and up and up until we come very close to achieving perfect accuracy, accuracy of 100%. the training score always goes up. On the other hand, we observe that as we increase the depth, the ability of the model to predict unseen data, so that's the test data, degrades, it begins to go down. So the question here, and really this is a very important practical question in machine learning, is how do we identify the optimal depth or optimal model complexity that will allow us to achieve the best prediction on unseen data? In this plot, we have some indication that the optimal model complexity might be, what is this, around 6 or so. It's just past 5 in the plot. But it's not completely sure. There's some randomness here that can corrupt our understanding because we randomly selected 30% of the data. Maybe if we had selected a different 30%, the story would look a little bit different. So there's a question about that. So for now, what we're able to observe is that overfitting can be a problem for us. It can afflict our models, even in real-world contexts. Okay, so we want to avoid overfitting in order to achieve better prediction accuracy. And we are going to need to do this essentially whenever we're deploying non-trivial machine learning models. In the next lecture, what we're going to do is we're going to take a bit of a systematic look at this and start asking ourselves, well, how can we more systematically evaluate the best model complexity in order to achieve strong predictive performance? Stay tuned.